In September of 2022, water rose as high as 15.5 feet above the ground inside a home on Fort Myers Beach, Florida. That's taller than a typical one-story roof. Almost none of that water was rain. Waves contributed, but the bulk of it was something else entirely. The storm that pushed it there was rated the same way every hurricane gets rated, by wind speed alone, the number stamped on every forecast. That number has never measured the thing that ends up killing the most people. Water does that job, and where it goes and how high it climbs follows rules most people never hear about. We rate hurricanes on the part that breaks things. The part that drowns people doesn't get a number. Most people treat the category number as the whole story. Category 1 sounds survivable, and Category 5 sounds catastrophic. That scale isn't wrong exactly, because it really does describe how hard the wind is going to hit a roof, a wall, a stand of trees along the road. None of that's exaggerated. A Category 1 can strip shingles and snap branches, and a Category 5 can tear the roof off a well-built frame home and leave a neighborhood uninhabitable for months. The wind half of the forecast earns its reputation. Ask what's actually responsible for the deaths once a hurricane makes landfall, though. And the honest answer runs almost entirely against what that scale implies. Wind is the headline number, the one printed on the map. It isn't the hazard responsible for most of the deaths, and it hasn't been for decades. Wind damage, as real as it is, turns out to be the least interesting part of what a hurricane actually does to the people in its path. The number on the forecast measures exactly one thing carefully and consistently, using instruments and a definition that haven't changed in decades. The thing that ends up killing the most people isn't that thing at all. The scale everyone quotes has an official name, the Saffir-Simpson Hurricane Wind Scale, and the word wind is sitting right there in the title, not as decoration. It measures exactly one variable, the storm's highest sustained wind averaged over a full minute. Forecasters clock it at 10 meters above the surface, about 33 feet up, roughly the height of a 3-story building. Category 1 starts at 74 miles an hour. Category 5 covers anything at 157 miles an hour or higher, with 2, 3, and 4 filling the range in between. Forecasters use that same 1-minute standard, whether they're calling a storm a strong Category 3 or knocking on the door of Category 4, because it lets every storm get compared on the same scale. The 1-minute standard matters more than it sounds like it should. It smooths out the shortest, most fleeting gusts and focuses on what a structure experiences continuously. That's useful for predicting roof and wall damage, and it says absolutely nothing about water. The National Hurricane Center is direct about what that number leaves out. Its own definition states plainly that the scale doesn't take into account other potentially deadly hazards, such as storm surge, rainfall, flooding, and tornadoes. That's not a caveat buried in a footnote somewhere. That's the agency that built the scale, describing its own limits in its own language. Elsewhere in the same guidance, it goes a step further. All categories of hurricane, not just the strong ones, can produce dangerous storm surge, rainfall, induced floods, and tornadoes. A Category 1 and a Category 5 are both fully capable of producing dangerous water. The number doesn't rule either kind of danger in or out. Local news coverage and even some older government bulletins have spent decades treating that single number as shorthand for total danger. That only reinforces the same assumption the agency's own definition contradicts. It wasn't always built that way. When engineer Herbert Saffir and Robert Simpson, who ran the National Hurricane Center at the time, put the scale together in the early 1970s, they didn't stop at wind. Simpson attached rough storm surge ranges and typical pressure numbers to each category. A Category 3, for instance, carried an expected surge of 9 to 12 feet, baked right into the label, roughly the height of a 1-story roof. The correlation simply didn't hold up under real storms. Storms sharing the same category kept producing wildly different amounts of water, depending on exactly where they came ashore. By 2009, the National Hurricane Center had begun phasing the surge ranges out, making the removal official in 2010. That year, the agency also gave the scale a more precise name, the Saffir-Simpson Hurricane Wind Scale, adding the word wind to stop people reading it as a water forecast. The agency put that word in its own name on purpose, after a public comment period, to make clear what the number actually measured. So the number on the forecast is honest about its limits, once you go looking for them. The water is where this actually goes next. People tend to picture hurricane water as one of two things: rain flooding a street or waves crashing on a beach. Storm surge is neither of those. Storm surge is the ocean itself, raised up and pushed inland by wind stress dragging across the water's surface. Meteorologists separate that from storm tide, which is the surge added to the normal astronomical tide. They separate it too from inundation, which is simply how much of that combined water ends up sitting on ground that's normally dry. The wind is doing almost all of the work here. It drags the surface of the ocean toward shore the same way a strong breeze drags the surface of a swimming pool. There's a second, much smaller contributor working alongside the wind. A hurricane's low central pressure lets the ocean surface directly underneath it bulge upward slightly, an effect meteorologists call the inverse barometer effect. Forecasters are clear that this adds only a small amount compared to wind stress, which is doing nearly all of the actual pushing, storm after storm. Look at how hurricanes have actually claimed lives in this country, and the ranking flips against what the category number would suggest. Edward Rappaport's analysis, published in the Bulletin of the American Meteorological Society, tracked United States tropical cyclone deaths from 1963 through 2012. Storm surge caused close to half of all direct deaths. Freshwater flooding from rainfall caused about another quarter, and wind itself accounted for roughly 8%. The most recent decade studied, 2013 through 2022, shows the same pattern with a shifted balance. Rainfall flooding accounted for nearly 60% of U.S. tropical cyclone deaths in that decade, while storm surge fell to about 1 in 10. That drop isn't because surge got less dangerous. Ian alone caused 41 of the 50 surge deaths since 2013, which means surge deaths are rare but catastrophic, concentrated in single events where the category number becomes almost meaningless as a warning. Hurricane Ian is the clearest recent example, and it's worth stating once, plainly, with the actual numbers. Ian made landfall in southwest Florida in September of 2022. The National Hurricane Center's official post-storm report attributes 66 direct deaths in the United States to the storm. 41 of those, the largest single category, came from storm surge, and 36 of those 41 surge deaths were concentrated in Lee County alone. The same report measured the surge at Fort Myers Beach at 10 to 15 feet above the ground, taller than the roofline of an ordinary single-story Florida home. Surveyors measured 15.5 feet above ground at one home and a still water mark 27 inches up on the second floor of another. That's the shape of the gap the wind scale leaves open. Water fills it, and the water isn't the same size everywhere a storm goes, not even close. It would be reasonable to assume a stronger storm just pushes more water everywhere in some rough proportion to its wind speed. That assumption is where the category number quietly breaks down. Storm surge height depends heavily on water depth, not only on wind. Oceanographic research on surge amplitude describes it as rising with roughly the square of the wind speed, while falling as the water gets deeper. Depth isn't a minor adjustment here, it's load-bearing. Double the wind speed against the same seafloor, and the surge doesn't just double, it can come close to quadrupling. Cut the water depth in half instead, with the wind held constant, and the surge roughly doubles. Not as extreme as the wind jump, but still a real lever, and it moves without the storm changing at all. A wide, shallow, gently sloping seafloor gives wind-driven water somewhere to stack up as it moves toward land. A narrow, steep seafloor pushes back against that same water and resists the buildup before it ever gets very high. Picture the difference as two ramps leading into the same ocean. One is a long, shallow boat ramp that barely rises for 100 yards. Water walking up it just keeps climbing higher, with nowhere else to go and nothing to slow it down. The other is a short, steep seawall, and water hitting it meets resistance almost immediately instead of room to spread out and pile up. That difference isn't hypothetical for Florida, it's the actual seafloor on two different sides of the state. The continental shelf fronting peninsular Florida's Gulf side, running from the Big Bend down past Tampa to Naples, is wide and shallow, the long ramp. The shelf off southeast Florida's Atlantic coast is steeper and narrower, closer to the sea wall. There's a strange twist buried in that same physics. The wide, shallow Gulf shelf that amplifies storm surge does the opposite job on wind-driven waves, flattening them out before they ever reach the beach. Along peninsular West Florida, the same shelf makes the surge worse and the surf calmer, for the same underlying reason, at the same time. Florida's coastline alone proves the original surge estimates wrong. A wide, shallow shelf sits on one side, a steep, narrow one on the other, and every coastline difference those estimates assumed away is sitting right here on one state's map. If that gap between what the scale promised and what the seafloor actually does is exactly the kind of thing you signed up to understand, subscribe to Florida Empire. There's a lot more Florida left to explain. This is the mechanism the category number simply can't see. Two storms of identical strength can flood a coastline to completely different heights, entirely because of which of those two seafloors they're pushing against. A homeowner watching two different storms approach on two different coasts is really watching two different physics problems, even when the wind speeds on the forecast look identical. The seafloor is only the first variable, because the shoreline itself does its own amplifying on top of it. An open, straight stretch of coastline lets storm surge spread out sideways as it comes ashore. That's one reason surge height along a straight beach tends to stay relatively even. A bay does the opposite. As a bay narrows, the same volume of water gets squeezed into a shrinking space, and it has nowhere to go but up. Think of it the way water behaves in a garden hose. Squeeze the opening and the water doesn't slow down. It sprays harder because the same volume is being forced through less room. A narrowing bay does the same thing to a wall of ocean water, just at a scale measured in miles instead of inches. Modelers describe surge amplifying as it moves up a narrowing estuary, and peer-reviewed modeling shows it rising rather than staying flat as the channel tightens. Tampa Bay works on the same principle, modeled explicitly inside Slosh's basin simulations. The bay narrows as it runs inland, and its shallow floor gives incoming water the same kind of ramp described in the last section. Surge moving into it doesn't spread out and lose height the way it might along an open beach nearby. It gets squeezed and channeled instead, funneled toward the low-lying shoreline at the upper end of the bay. Near Pensacola, the narrow northern reaches of Perdido Bay, Escambia Bay, and East Bay produce the same effect, funneling water north into low-lying river valleys that have nowhere left to drain. A real demonstration played out on that same stretch of coast 16 years apart. Hurricane Ivan made landfall at Gulf Shores, Alabama in September of 2004 at 120 miles an hour, a Category 3. It pushed a surge of 10 to 15 feet from Pensacola to Destin, over the roof of a one-story house and well into the second floor of a two-story one. Hurricane Sally hit the exact same coastline in September of 2020 at 105 miles an hour, a strong Category 2. Its surge ran 3 to 6 feet on the open Gulf-facing beaches, roughly waist-deep to over your head on a person standing at the waterline. The weaker storm's worst water didn't hit the beaches at all. It piled into the back bays and sounds of southeast Baldwin County and the northern ends of Escambia and Blackwater Bays, where surveyed inundation reached 7 to 9 feet above ground, with torrential rain adding to the total. Same coastline, one category apart, completely different water patterns. Ivan was bigger and faster, pushing a broad wall of water onto the open coast. Sally was smaller and crawling at 3 miles an hour, so it poured water into the bay systems instead. The difference came down to the storm's size, speed, and track, not its category number. The direction a storm travels matters here too, not just its strength. Research on bay systems backs this up. A storm tracking inland, straight toward a bay, tends to produce meaningfully more surge inside that bay than one traveling parallel to the shoreline. The wind direction relative to the bay's shape is what does the funneling. Track matters as much as category, sometimes more. It's the same wind speed on the forecast, whether that storm is aimed at 40 miles of open, straight beach or the narrow throat of a river valley, and the water piles up completely differently depending on which one it hits. Both the seafloor and the bay are permanent features of the map, set long before any storm forms. The next variable isn't fixed at all, and it runs on its own clock regardless of what the storm is doing. Storm surge on its own isn't the full flood story. It rides on top of the ordinary astronomical tide that rises and falls every single day, whether a storm exists or not. The sum of the two is called storm tide, and that's the number that actually determines how much water reaches dry ground. On Florida's Gulf Coast, the ordinary tide range is small, about plus and minus a foot and a half in Tampa Bay. Against 15 feet of storm surge, the tide is a modifier, not a make or break variable. Astronomical tides aren't constant either. They swing to their widest range during new and full moons, when the sun, the moon, and the earth line up, and their combined pull on the ocean peaks. Hydrodynamic modeling of surge moving through coastal waterways shows the timing between surge and tide can shift the total water level by a meaningful amount, even when the shift itself is small. Waves add a third layer on top of both of those. As wind-driven waves approach the shore and break, they push additional water onto the coast. Oceanographers call this wave setup, and it stacks still more height on top of the storm tide that's already there. It's a smaller contributor than surge itself, but at landfall, it isn't nothing. It's one more reason the water at the shoreline runs higher than the surge number alone would suggest. Add the surge, the astronomical tide, and the wave setup together, and only one of those three, the surge, has anything to do with the storm's wind speed at all. The same storm making landfall at high tide versus low tide on Florida's Gulf Coast could see a difference of 2 to 3 feet in total water height. That's real, but it's smaller than the margin created by the seafloor or the bay shape. Forecasters watch the lunar calendar for exactly this reason as a storm approaches. The same wind field, the same seafloor, and the same bay can produce a noticeably different total water level, depending only on whether landfall lines up with a slack tide or a peak one. That's a purely celestial mechanism folded into a hurricane forecast, and it's as far from the category number as this gets. Wind speed says nothing about where the moon happens to be that week. Put the seafloor, the bay, and the tide together, and they don't distribute evenly across Florida's coastline. They stack harder on one side of the state than the other. Every mechanism explained so far could technically apply to any coastline in the world. Applied specifically to Florida, the weight falls unevenly, and that's the point where this stops being generic physics and starts being a map. The Gulf Coast combines the wide, shallow shelf described earlier with more of the low-lying, funnel-shaped bay geography that amplifies surge the way Pensacola's bays do. The Atlantic coast, particularly southeast Florida, sits mostly on the steeper shelf that resists surge buildup in the first place. Put plainly, the state has one coastline built to hold water in and another built to push it back out. Stack those two effects together, and the reason becomes mechanical instead of mysterious. The Gulf's shelf is the long, shallow ramp from earlier. A disproportionate share of its coastline also funnels through bays and river mouths, squeezing that water even higher before it ever reaches land. The Atlantic side of the state gets the steeper shelf and considerably less of that funneling geography, so the same wind speed simply has less to work with once it gets there. This is why the Gulf Coast, including Florida's Gulf side, consistently produces some of the country's worst storm surge events, independent of any individual storm's category. A moderate Category 2 storm making landfall against that shallow Gulf shelf can, in principle, put more water on the ground than a considerably stronger Category 4. That stronger storm just needs to make landfall somewhere with a steeper shelf and a straighter shoreline. The difference comes down to the ground, not the wind speed. None of this means the Atlantic side is immune. A powerful enough storm can still push dangerous surge against a steep shelf. A direct hit on a bay or inlet on that side of the state produces its own funneling effect, regardless of which ocean the storm came from. What differs is the baseline. The Gulf Coast starts every storm season carrying a structural disadvantage the Atlantic coast doesn't have to overcome, before a single storm has even formed that year. That's not something wind speed measures, because at that point it isn't measuring the storm at all. It's measuring the ground the storm happens to be arriving at. That's a completely different question, with a completely different answer for every mile of coastline, even when the wind speed on the forecast stays exactly the same. If geography decides the outcome and the wind scale can't see geography, something else had to be built that could. Go back to that number from the opening, 15.5 feet of water above the ground at Fort Myers Beach, taller than an ordinary roofline. Every mechanism since then explains exactly why that number landed where it did, and not somewhere else. The wind scale left a gap, describing speed and nothing more. Water filled that gap and did most of the killing. The size of that water came down to three compounding physical variables. The seafloor shallowness was one. The coastlines funneling through a bay was another, and the last was where the tide happened to sit on the clock. Those three variables aren't random. They stack harder on Florida's Gulf Coast than on its Atlantic side, which is why identical storms can produce wildly different outcomes depending on which shoreline they hit. That split mirrors a bigger shift in how these agencies think about risk generally. The original scale tried to bundle wind and water into one convenient number, and separating them later wasn't about making things more complicated for its own sake. It admitted that a single number can't carry two physically different hazards without hiding one of them. The National Weather Service built a system specifically to answer what the category number can't. It's called SLOSH, short for Sea, Lake, and Overland Surges from Hurricanes. SLOSH was developed at the National Weather Service by a team led by Chester Jalesniansky, and Florida's regional planning councils use its output to draw the state's actual evacuation zones. SLOSH grids are built from the exact variables this video just walked through: coastline shape, bays, rivers, water depth, even bridges. The model runs simulated storms from every compass direction at every category, then combines all of those runs into a single worst-case map. The output of all that modeling isn't a single number the way a category is. It's a shaded map, color-coded by how many feet of water above normally dry ground a given block could see. That gets translated into a zone letter that tells a resident whether they sit in the water's path at all. That's the same unit this video opened on, feet of water above the ground, not a category, because that's the figure that actually decides whether a home stays dry. A category describes the storm. A surge zone describes the ground. Slosh models lake surge too, and Florida is why that isn't an afterthought. In September of 1928, a hurricane crossed Lake Okeechobee. Its winds shifted from northerly to southerly, sloshing the water first against the southern levees and then across to the northern ones. The dried mud levees failed on both sides. Surge inundated Belle Glade, South Bay, and Okeechobee City. Estimates put the death toll in the thousands. That's the single deadliest hurricane in Florida's recorded history. And the surge came from a lake, not the ocean. Florida's evacuation zones are drawn from that water modeling, combined with practical safety factors, like whether a road could get cut off by rising water. State and local emergency management agencies handle that work. The National Hurricane Center introduced 2 specific products to close that gap. In 2014, the agency launched an experimental real-time potential storm surge flooding map, a color-coded forecast of how far inland water could reach. 3 years later, in 2017, they added official storm surge watches and warnings, operating on the same logic as a hurricane watch, but for water, not wind. Both products postdate the wind scale by decades because the agency had to build new products on top of it before it could measure what the category number had always missed. None of it is drawn from the category number at all. That's the direct, built, engineered answer to everything this video has explained, a whole planning system constructed around the hazard. The wind scale was never designed to see. The category number answered the wind question the whole time, and the water question needed an entirely different system to answer it. Emergency managers' instructions for anyone watching that zone are straightforward. Run from the water, hide from the wind. That's the pattern behind most of what looks simple on Florida's coastline, a system built on purpose, once you know where to look. Subscribe to Florida Empire. There's a lot more Florida left to explain, and none of it is as normal as it looks.